Hello, my name is Jae Baek. I'm currently a master's student at Seoul National University in Seoul, South Korea. In this presentation, I'm going to introduce an assay that I developed for label-free nucleic acid detection with single nucleotide specificity. Current nucleic acid-based detection techniques are largely classified into two groups, qPCR and isothermal amplification. qPCR, or real-time PCR, utilizes thermocycling to derive exponential amplification. It detects a target with high sensitivity and selectivity by measuring real-time fluorescence of probes. You may already be familiar with this technique from the SARS-CoV-2 pandemic. While qPCR offers excellent performance and well-established protocols, it has some limitations. First, it requires expensive equipment, such as dedicated thermocyclers. Second, the qPCR process is time-consuming, often taking up to an hour and a half to complete. To address these drawbacks, isothermal amplification techniques has been developed. These methods use enzymes and specialized primer pairs to drive amplification at constant temperatures, eliminating the need for thermocyclers and offering much faster kinetics. However, isothermal amplification techniques often face challenges such as false positive signals due to imperfect enzyme fidelity and primer dimer formation. To overcome these issues, we have integrated single-strand conversion and SEA probe-based detection steps, which is a novel approach that has not been previously demonstrated in isothermal amplification. We developed a new assay called Classic, combination of light-up aptameric probes for high specificity and sensitivity with isothermal amplification and single-strand conversion. First, target DNA strands are amplified through recombinase polymerase amplification, or RPA. Here, I'd like you to note that the 4' has phosphodiephone at its 5' end, which becomes important in the next step. Second, T7-exonuclease is added into the mixture. This enzyme digests any DNA strands but those derived by the 4' with phosphodiephone. Through this selective digestion, we can convert double-stranded amplicons to the single-strand targets for sequence-selective hybridization-based detection in the next step. Finally, a pair of split dipoxyl aptamer probes and a fluorogenic dye called aramino are incubated with the single-stranded targets. Only when the probes bind to the target strands, a dipoxyl aptameric core forms, which captures and activates aramino, thereby reporting the presence of the target nucleic acid. In our first set of experiments, we tested the sensitivity of Classic using synthetic fragments of the catchy gene and genomic DNA of Mycobacterium tuberculosis as targets. Both sets of results demonstrate that Classic can detect targets at concentrations as low as 10 attomolar for the synthetic target and 10 copies per microliter for genomic DNA, showcasing its high sensitivity. We also investigated the selectivity of Classic using 3 homologous DNA strands. The catchy strand is perfectly matched to the binding arm of the upstream STA probe, whereas GC has a single base mismatch and the triple W has a 3-base mismatch to the probe. The results were quite striking. Despite the close sequence similarity, only the perfectly matched catchy showed a significant enhancement in AO fluorescence, while the others exhibited values similar to the negative control. This indicates that Classic is a highly sequence-selective assay capable of differentiating single nucleotide mismatches. In conclusion, we developed Classic to address the current challenges of isothermal amplification, enhancing selectivity and expanding the application of SDA probing system to DNA detection. The binding arm sequences and primers can be redesigned to analyze various DNA biomarkers. Our future work will focus on incorporating multiplex detection and tuning Classic for RNA analysis. Thank you for watching.